In our last lecture, we were discussing about the stereo geometry, and there we had seen that how to recover the depth information which is originally lost in the two-dimensional projection of a particular scene, and how to recover that using two views. And we had considered the lateral stereo geometry model, in which we had assumed that the two cameras, the left camera and the right camera, are displaced with respect to each other in the x direction. So primarily we had assumed a distance of separation delta x between the left camera and the right camera, and we had obtained the expression for the unknown depth in terms of the focal length of the camera, the distance of separation, and the relative shift in the position of the corresponding image point in the left view and the right view. So we had got expressions like this, where the Z0 which we have over here, the Z0 was written in terms of lambda, delta x, xl and xr, where xl and xr are the positions of the image point as reference to the left camera's coordinate system. And since the displacement is delta x, so xr plus delta x basically gives us the point which we are seeing on the right camera, but with the del x displacement added, it gets translated to the left camera's corresponding point, and xl minus xr plus delta x is giving us the shift. And it is this shift or the displacement which is described in the literature as disparity. The term which we very often used in literature is called disparity, and primarily disparity means it is the same as this xl minus xr plus delta x. This gives us the disparity. So what we had obtained in the last class was that the unknown depth Z0 was inversely proportional to the disparity, xl minus xr plus delta x. And we had considered the geometrical arrangement of this nature. So we had the left camera coordinate system x, y, z, the right camera's coordinate system x prime, y prime, z prime, their relationship being just in the x direction there is a displacement by an amount delta x, okay, and we had an unknown point P over here, and P's image and corresponding to P, the image points were PL having coordinates xl, yl in the left camera, and PR is the corresponding point in the right camera with coordinates xr and yr. So with respect to this PL and PR, we had done our analysis. Now a question that arises is this, that if supposing we have located a particular point PL in the left image, alright, and we would like to determine the unknown point P, the depth for the unknown point P we would like to determine, but we know only PL. Now that means to say that if we want to determine the depth of the unknown point P, what we must do? We must find out its corresponding point PR in the right camera. Alright. Now if we want to search for the corresponding point PR in the right camera, the pertinent question that comes to our mind is that over which region are we going to search for it? Alright. The question that we have here is, if we have the left image over here, and if we have the right image over here, and if there is a point PL in the left image, then we have to find out the corresponding point in the right image. But without putting any constraint, what we can say is, if we want to search for a corresponding position of PL in the right image, then we should search over a two-dimensional space, isn't it? Because the point can lie anywhere on this two-dimensional plane on the right camera. So if there are n number of pixels in the x direction and n number of pixels in the y direction, then over n square number of pixels we have to make a search. But just think about it. If such a kind of search we have to do for every such points, okay, every such candidate points from the left image, because PL is not the only point that we have in the left image. There may be a lot of other points as well in the left image, and we would like to search for all these points coming from the left image. We have to find out its corresponding position in the right image. So for every such candidate we need to search over a region of n by n pixels, that is to say over n square pixels, and our computational complexity in that process is going to be extremely large. So now what we have to think over is that, can we reduce this much of computation? Can we simplify our search range? That is what we are going to discuss in today's class. Now let us go back to our diagram which we had presented in the last class. Now we have a point PL over here, and corresponding to the point PL, okay, we are having this PL and this CL. CL is the optical center of the left camera. PL and CL we are joining, and we are extending this straight line. Now this straight line, or rather the ray, is naturally a straight line in the three-dimensional space. Now obviously one physical constraint that comes about is that corresponding to this, that the corresponding image point PR in the right camera, okay, its position in the three-dimensional space should be lying somewhere on this particular straight line. Now that means to say that we have to determine that this particular ray which we have, by joining PL and CL and extending this ray, we do not know where this point P is, okay. If we extend this ray PL CL, okay, then for this ray what is going to be the corresponding image in the right camera? Can anybody tell that what is going to be the corresponding image for this three-dimensional straight line in space? Is it going to be a point? Is it going to be a region? Or is it going to be a straight line? Excellent. Somebody has given the correct answer that it is going to be a straight line. Basically we have a ray joining PL and CL, and this particular ray will be mapped in the right camera as a straight line. So obviously if we are searching for the corresponding point of PL, okay, on the right camera, if we are searching over the entire n square region, okay, we are making some wasteful efforts, isn't it? Because after all we know that this will be mapped into this straight line in three-dimensional space will be mapped into a straight line in the 2D space. So naturally we have to search only over a straight line, but we have to think over that what kind of straight line will that be. Should that be a straight line? If we have the point PL over here, should the straight line be like this, or the straight line will be like this, or the straight line will be horizontal like this, or the straight line will be vertical like this? Unless I don't know anything about the nature of the straight line, again I am not making a good use of the search space. So I have to make sure about the nature of that straight line. Now again I go over to the camera geometry which we considered in the earlier class. The camera geometry considered is pretty simple. the two cameras, okay, are looking straight with their z axis, okay, absolutely parallel to each other. They are absolutely looking straight, and on this type of a geometry, if we have a point PL, okay, on the left camera, and we are joining P, then what will be the nature of the straight line for PR? Can anybody predict? Somebody has said that the straight line on which the corresponding point PR must lie will be a straight line parallel to x-axis. That is what somebody has predicted. Let us see whether that prediction is correct or not. I again go back to the relationship which we had in the last class. For the left camera, this is the relationship we got. x0 by xl was equal to y0 by yl, and that was equal to lambda minus z0 by lambda. And for the right camera, we had obtained this particular expression. Now, just look at it. Just look at this particular portion. We have y0 by yl is equal to lambda minus z0 by lambda. y0 by yr is equal to lambda minus z0 by alpha, by lambda. So obviously, what is the immediate conclusion that we are having? YL is equal to YR. So if YL is equal to YR, in that case, what he said is correct. That is to say, if the point PL is having its Y coordinate as YL, okay, then the corresponding point PR is going to have a coordinate YR which is equal to YL. So that means to say that the search region is going to be a straight line which is parallel to the x-axis, because the y coordinate for the left point and the corresponding right camera's point, they are going to be the same. We have already determined that YL is equal to YR from these equations 3 and 4. YL is equal to YR, and as a result of that, the corresponding search region for PL in the right camera is going to be a straight line. So which means to say that if I have in the left camera a point PL like this, then the corresponding point PR must lie along this straight line. Alright. So which means to say that now our search is not going to be over n by n number of pixels, but the search is going to be over only n pixels. So I have reduced the search region. Now somebody can still say that, is there any further simplification that we can do whereby I can constrain my region of search further? The reason why I am telling it is that on a particular, for a particular y, okay, let us say that on the left camera I have, let's say, these many 6 or 7 points. Actually, typically the number of points will be much more, but let us say that we have these many points on the left camera and we have to search for the corresponding point in the right camera. So if for every point I consider a region of n, okay, then there is also a possibility that if these are the points on the right camera, then which corresponds to what? Which point corresponds to which point of the right image? Okay. If we make any mistake in finding out that, then that gives rise to a false matching between the between the left image's candidate point and the right image's candidate point. And obviously, if there is such false matching, it gives rise to a false depth value. And false depth value obviously means that it gives me an erroneous three-dimensional profile. Alright. So, naturally, in order to reduce such false matches, what I should do is that if for a particular candidate, I know what is going to be my search range. If the search range is further constrained, okay, then possibly finding out the corresponding point. Okay, in the process of finding out the corresponding point, we will be making less of mistakes. Okay, there are less chances of false matching if the search region is further constrained. That is the first advantage. Second advantage is, of course, if the search region is less, if the search region is even less than n, that's what we are trying to tell over here, then the total computations which are involved, that's also less, so that the entire process of stereo matching will be faster if the search region is less. So let us see how to reduce that search region. Now again, I considered the same camera geometry, that is to say, this is the left camera's coordinate, this is the right camera's coordinate, P is the point in space, and now without making any loss of generality, okay, we can consider the XZ plane alone, and on the XZ plane, okay, we can do the geometrical analysis to find out the search region. Let us say that even the point P is also lying on the XZ plane. If we do that simplifying assumption, then we can see that how to obtain the search region under the constraint case, and this we can do, of course, without any loss of generality. So let us have the diagram. So this is for the left camera, and let us say this is the right camera's position, and I am assuming the x-axis in this particular direction. So this is the direction of x-axis. IL is the center of the left image's plane, okay. IR is the center of the right camera's plane, and on this direction is my z-axis. So this is the z direction, and I have assumed the point CL, that is the center of the left image's the center of the left camera's optical center for the left camera is CL, and for the right camera the optical center is at the point CR, and I have considered that their focal lengths are equal, and focal length is equal to lambda. So this is lambda, and lambda is equal to focal length, and it is equal for the left as well as the right camera. Now I consider a point PL over here, PL on the left camera. So let me now extend PL with CL, all right, and I don't know where this point P is in the three-dimensional space, so I will complete this ray little later. Now all that I can say is that this point PL is going to lie within this limit and this limit for the photographic plate. So I have assumed that this is this point, the extreme left side point is L and the right side point is E for this left camera. Okay. So if I now extend this L with CL, and if I extend E with CL, then one thing which I can say is that this point PL is going to lie over this region. I mean, it will be bounded by this ray and this ray, because this ray is for the extreme left side point and this ray is for the extreme right side point for the left camera. So this ray will be contained within this zone. All right. Very similarly, for the right camera, our situation is like this. All right. Let us say this point is T and this point is R. Okay. So that any point PR that lies on the right camera should be in between this T and the point R. IR is the optical center. Now, I extend this ray from PL further. Now tell me, if the point P happens to be somewhere over here. Let's say I have the point P over here. In that case, will it be seen by both the cameras? No. Certainly not seen by both the cameras, because if I extend this point P, if I take this to be the three-dimensional point P and I extend P with CR and proceed, okay, that intersects this plane outside the visibility zone of the right side camera. So because we have considered the extreme limits of its dimensions T and R, okay, so that is the reason why I will not be able to see this particular point P on the right camera, but I am seeing this from the left camera. So it means to say what? That for this particular point we are unable to get a binocular view, or we are unable to get a stereo view, because it is not being seen by both the cameras. But if the point P lies exactly over here, what do you think will be seen on the right side camera? Extreme right. So the correct answer that has come from the class is that if the point P is over here, then by joining P with CR, I get this point R. That means to say that the corresponding image point on the right hand side is on R. Okay. So that means to say that the point has become just visible. If I consider the point P over here, what happens? Is the point visible or not visible? The point is visible in the right side image also, isn't it? Let us say I have the point P over here, okay, and I join P with CR, sorry, and this is the position where I have PR. If the point P is actually lying over here, okay, that is to say, if the point P is lying over this zone which I am shading over here, if the point P lies on this zone, okay, then we can see it from both the cameras. All right. Now let us say that this distance, I mean that both these photographic plates are having a width of h, so that from this point to this point I have got a width equal to h by 2. So this is h by 2. This distance is also equal to h by 2. Okay. So if we do that, then we have the following bounds for XR. Given a particular point PL, okay, we can have these limits for XR. We can write that XR is going to lie between XL minus delta X and minus delta X plus H by 2. This is going to be the limits for XR. I will tell you how it comes. What is the distance between CL and CR? The distance of separation between this Z axis and the Z prime axis for the right camera? Delta X. So this distance is delta X, and this being the positive X direction, this distance is actually minus delta X. And if I go to minus delta X minus H by 2, what do I get? I get this extreme point R over here. Alright? So minus delta X minus H by 2, that means to say that this expression which I have written, minus within parenthesis delta X plus H by 2, gives me this position R. So this limit, this particular limit, I am getting when the image is at this point R. Is that clear? And what is the other limit? Can anybody tell me? I mean, if PL is known to us, okay, can anybody tell me that what is going to be the other limit? Is it T or something less than T? Something less than T. Why something less than T? If PL is the corresponding point, okay, what is going to be the corresponding point PR? Can PR lie on T? Why can't it?
So because the region in which the image is seen by both the cameras is something less than.
Well, this is the region in which it is seen by both the cameras. So I can extend, I mean I don't have space to show here, but I can extend my ray farther and farther on this particular region.
Same point, draw the distance h by 2 minus x.
Yes.
That is the distance from L to PL. If you, that much of distance you have to take it off from T. So till that such point the image will not be there. That means from point T, if you travel a distance equal to LPL. So
Okay.
that distance is nothing but h by 2 minus x.
Okay, I think the correct thinking is obviously there. Now let us consider that what is going to be the extreme limit. In the extreme limit, this point P is going to lie at infinity. And if the point P lies in infinity, in that case, okay, the disparity or the displacement is going to be 0. And if the displacement is going to be 0, then this distance LPL will be equal to the distance TPR. So we must have this point PR, okay, at such a position in the limit such that the distance TPL and the distance TPR and the distance LPL should be equal. And it is based on this constraint only that we have got the other limit as XL minus delta X. Obviously, this point is XL with respect to IL. IL is the center of the the coordinate center. So with respect to IL, this is XL. Point PL is XL. And if I go by a distance XL minus delta X, I land up in this point PR such that TPR is equal to LPN. Is that clear to all of you? So, this is the limit that we have got. So, we have to search not over the entire n pixels on the horizontal axis, rather instead of searching over the entire number of pixels, instead of searching over this entire horizontal scan line within a distance TR, I should rather search for a distance PR and R, which is less than TR. Alright. Now here, one assumption which I am making is that this point P, okay, can lie at infinity also. Now, in many of the practical situations, we do not have object points, okay, whose z coordinate is at infinity, but rather we can, it is quite reasonable to assume in many of the practical cases some upper limit of depth. Like I can say that if I happen to draw a line like this and say that this is going to be my Z max, okay, the maximum depth, then obviously our search region will get further reduced, isn't it? Alright. Now before we go into that analysis, we will do that also, that assuming some upper limit of Z, okay, what is the search region that we get? Before we do that, it is also interesting to do one more analysis. Can we determine the depth of this point P if its depth is less than this much of distance? So I have assumed this distance to be a distance D, and if the Z coordinate of the point P is less than this D, okay, which I have written, if it is less than D, then I cannot see this point P from both the cameras, and if I can't see the point P from both the cameras, obviously I can't determine the depth. So if I tell that this point of intersection of this ray LCL and RCR, okay, both extended, I assume they are intersecting at the point S. So if the distance from S to this position is equal to D, then this D is the minimum depth for the point P. So I can write this as D min, alright, and if this is equal to D min, okay, if this distance is equal to D min, then from this diagram, okay, I can say that the Z0, what is Z0? Z0 is the depth of the point P. I have assumed that the point P is having a coordinate x0, y0, z0. So z0 is the unknown depth. So obviously z0 is going to be greater than or equal to, let us not assume this distance of d min, okay, d min is the minimum depth, and we also assume this distance. Let us call this distance to be d1. That is to say, from the optical center of the camera to this point S, this distance I am calling as d1. Alright? So that my z0 has to be greater than or equal to d1 plus lambda, because d min is nothing but d1 plus lambda. So z0 is greater than or equal to d min, rather I can write it as d1 plus lambda. And what is d1 in terms of the known parameters? Lambda is known to us, delta x is known to us, and h is known to us. What is d1, okay, in terms of lambda, delta x and h? Can anybody tell? This is clear from this geometry. Alright, take this triangle. All right, this triangle is having, I mean, take these two triangles, this one and this one, that is SLR and SCLCR. Take these two triangles. The distance from L to R is lambda x plus h. The distance between CL to CR is delta x, okay, and this is delta x plus h. L to R is delta x plus h. So from these similar triangles, okay, it is possible to deduce that D1 is equal to, you can verify this, D1 is equal to lambda into delta x divided by h. Is that correct? Okay, so you have already verified. This is equal to lambda into delta x by h, so that the minimum depth, okay, Z0 can be written as lambda delta x divided by h plus lambda. So this expression is very important, that if the point P is having a depth beyond this, then only you can try to recover its depth, depth from the two views. Then only, because then only it will be visible from both the cameras. Now I have assumed some maximum depth. Instead of calling this as Z max, let me call this as D max. So D max is the maximum depth for the point. So D max is the maximum depth for point P. Okay, if we do that, then again from the similar triangles, okay, you can find out that the search region becomes now, obviously on this side the limit is still this point R, okay. Even if I assume a maximum depth over here, okay, still my extreme limit on this side is that the image can be at the point R, because if this is the ray, then I have the image point at R, okay. But all that I am doing is that instead of assuming the depth to be infinity, I am assuming the depth to be at the point, the depth to be less than infinity, so that the corresponding image point will be lying to the right of this point PR. So the search region will be little less, and it is less by this much of amount. Of course, on this side the same limit holds good. For this point R, the limit is minus delta x plus h by 2, and on the other side we have XL minus lambda x. XL minus lambda x we had got for the point PR. You remember, for the point PR we had got XL minus lambda x, but assuming a maximum depth D max, we will be getting this as lambda into delta x divided by D max, okay. And in this expression, lambda is positive, delta x is positive, D max is positive, so that we have to, so that this expression will be less than XL minus delta x, and as a result of that, okay, our total search range is going to be less as compared to the original search range of PRR, okay. Is this clear to you? So we will have the point now at PR prime, and for PR prime this is the limit XL minus delta x minus lambda delta x divided by D max, and we have PRR, okay, should be greater than PR prime R. So as a result of that, because PR prime R is less than PRR, okay, the search region is less. All right. Any questions or difficulties? All right. Somebody wanted me to repeat the last part. What we are having is, in the earlier case, our limits were, means when we permitted the point P to lie at infinity, the limits were between minus del x plus h by 2 and xl minus delta x. Okay? When we permitted infinity depth, but when I am permitting a maximum depth d max, in that case the limits change. The limits on this side doesn't change, it is still minus delta x plus h by 2, but on the other side it becomes xl minus delta x minus lambda delta x by d max. And obviously you can clearly see from here that the image point, okay, corresponding to PL, the point in the right image is, if its point is at PR prime, then this PR prime is going to lie on the right of this point PR. So as a result, the search region now is the distance R PR prime instead of R PR, and R PR prime is a distance which is less than R PR. R PR prime is a distance less than R PR. Okay, so we have reduced the search zone. All right. Any doubts?
If there are multipoints between R and PR, which will corresponding to the particular multipoints in also first plate, what would happen? How can we map to 1 to 1?
Okay, it's a very interesting question somebody has asked. The question is that in between this zone RPR, we are having multiple number of points, and we have to decide about the point corresponding to PL. So how to decide? Well, the task is not an easy task, and mind you, it will be so in all practical cases. It will be so that within the zone RPR we will be having such multiple number of points really. So we have to avoid false match and choose the correct one. So we have to go over to the topic of stereo correspondence, of stereo matching, in order to properly answer this question. But since we are not going over to the since we are not discussing about stereo matching over here, okay, let me tell you very briefly what is normally done. What we do is, we take, whenever we are considering this such points PL and all the other candidates from the left image, naturally those points are some points of interest for the object. So corresponding to those points of interests, there will be some specific features. Specific features means intensities. Its intensity is on the left hand side, its intensity on the right hand side, okay, or they may be just the set of boundary pixels, that is to say only the edge pixels. So there may be features of this kind, and we will be matching featured points with featured points, and that is why whenever we have such kind of multiple candidates, okay, within which we have to decide the correct match, for such kind of things, okay, we have to take the feature property also into account. The feature parameters also should be kept under consideration, and the matching, okay, will be done based on such feature parameters, okay. Wherever we find the maximum feature parameter similarity, okay, amongst the, supposing in between the region RPR I have 5 candidates, okay. So in order to decide that which one out of these 5 candidates will be the matching for this point PL, all right, I will see that which is the point that gives best parameter matching, okay, and I will choose that point only, all right. But that is the subject of stereo matching, or what is known as stereo correspondence, and it is quite an involved subject, and we are not covering this stereo matching under the digital image processing course over here, okay. But lot of useful references are available, okay, on stereo correspondence. So any other questions? Okay, now let me also tell some particular observations. All right. Now, one thing, that let us say that we have some maximum depth. So we again consider this kind of a stereo geometry. So this is the left camera, IL center, this is the right camera, IR center, this is CL, this is CR, okay. They have the distance delta x in between them, and I have assumed that this is the maximum depth, okay. That is to say that I have this distance equal to d max. All right. Okay, last time I think we had considered this d max. Okay, I made a mistake. Actually, this d max which I had defined, okay, please make this correction. This d max which I had defined should not be defined from this point to this point, but from this distance of optical center. So this is not correct. So I should have this distance as d max. This is CL, this is CR. So from this line to this line is my d max. Only then the expression which we had shown, okay, will be correct. So I am assuming this to be d max, and this is the, let us say that we have a point r prime over here, and we have a point L prime over here. All right. And right. I think it's a bit involved diagram. Okay. Okay, I mean, there should be an attempt to redraw this. Without that, I'll not be able to show it fully. Okay, now I can show. So this was my point S, that is L. This I have considered to be L, this is CL, and this I have considered to be R, this is CR. So the ray joining RCR and LCL, they are intersecting at this point S. So which is the zone visible to both the cameras? Obviously this zone. All right. Now just see if I consider some point P over here, okay, if the point P lies in this zone, then it is visible to both the right and both the left and the right camera. But if it is on this side, then it is not visible to both. Now, if we take this point to be R prime and we take this point to be L prime, and this is already S, so whatever is visible within, if the point P lies within this zone R prime, L prime, S, okay, only then it will be visible to both the cameras. So now I join R prime with CL, and supposing here I got a point which I call as R double prime. Now if the point PL, okay, if the point PL lies within R double prime E, okay, what can you say about this point PL, or what can you say about the corresponding three-dimensional point P? If PL lies within this zone R double prime E, it can't be seen by both the cameras. So that means to say that the moment I find that the point PL lies within R double prime E, I can immediately conclude that this point will not be visible to both the cameras. So this is not our binocular point. Now, if the point PL lies within L and R double prime, are you sure that this will be visible to both the cameras? Why not? Yes, somebody has told correctly that if I have the point PL between L and R double prime, there is no certainty that it will be visible to the right camera also, because the point P, supposing this is PL, and the point P can lie on this zone, that is, it may lie within R prime CL S, and if it lies within this zone R prime CL S, then it will not be visible to both the cameras. Supposing the point P lies over here, okay, R prime S L prime, do you think that this will be always visible to the right camera? If the point P, just I repeat my question, if the point P lies within the zone R prime S L prime, is it visible to the right camera also? Always? Always. Somebody has given the answer always, but let us think about some possibility like this. So, always means what? Fine, I can join this ray P, from P I can join CR, and the point where it intersects this, okay, this will give me the point PR. Now supposing I have some obstacle over here. Supposing I have an obstacle on this region, okay, then can you see the point P? You can't. The ray from P to CR, okay, that itself is getting blocked over here, and we will not be able to see this point P. So don't think that if the point P lies within this zone R prime S L prime, it will be visible to both the cameras. It will be visible to both the cameras provided there is no obstruction, or what is described in the literature as occlusion. So whenever you have occlusions, then you can't have a view of the, you can't have a second view. Okay? So this is one interesting observation, and we will conclude our discussions on stereogeometry in the next class, in which we will see that how to decide about this delta x. This was our distance delta x, and we will see that if we make delta x too small, then what happens, and if we make delta x too large, then what happens. This is what we will discuss in the next class, and then we will introduce the next topic. All right? Thank you.